All right, so today we're diving deep into the world of alternating current, AC for short.
Oh, AC, it's everywhere, isn't it?
It really is, and we've got these two excerpts. One is Alternating Current 2018.pdf,
Okay.
and the other is Chapter 12.pdf.
All right.
And we're going to kind of go through those and really just try and give everyone a better understanding of how AC works,
Yeah.
whether you're, studying this for school or just want to brush up or just curious.
Right, exactly. Or fix something. I don't know.
Yeah, who knows, right? So I guess first, to get started, like when we hear about electricity, we also hear about direct current, DC, so like batteries and stuff.
Yeah.
What is the actual difference between like DC and AC?
Well, in DC, the current flows just in one direction, so it's a one-way street.
Okay.
And with AC current, it actually reverses direction periodically. So it's like a busy street with traffic going back and forth.
Huh, okay.
And that's what makes it alternating.
Ah, that makes sense.
Yeah.
I see. So, and then the excerpt mentioned that AC is the main way we transmit electrical energy.
That's right.
So how come that is?
Well, that's where Nikola Tesla comes in.
Oh, yeah, Tesla.
The genius, the father of alternating current.
Right.
He was really the one who championed the AC approach over Edison's DC approach. And for good reason. I mean, think about it. AC has the ability to change voltage levels efficiently using transformers. It was a game changer.
Oh, transformers. So like those big metal boxes on like telephone poles and stuff.
Exactly. They're like electrical gear shifters.
Okay.
They let us increase the voltage for long-distance transmission
Oh,
with very little energy loss, and then decrease it again for safe use in our homes and offices.
I see.
So it's kind of like, imagine trying to send power across a country on low voltage. It would be like trying to water your garden with a tiny straw.
Yeah, that's a good analogy.
It just wouldn't work, right?
Right.
So Tesla his vision really paved the way for widespread electrification.
Okay, so how does an AC generator work? Because sometimes it's called an alternator, I think.
Right.
How does that create this back and forth current?
Well, picture this. You have a loop of wire, and it's spinning inside a magnetic field.
Okay.
And as that loop rotates, it cuts through the magnetic field lines, and that induces a voltage,
Okay.
which causes the current to flow.
Okay, so it's the loop spinning inside this magnetic field.
Right.
What makes the loop spin?
Well, that's where we need a source of mechanical energy.
Oh.
And AC generators can be powered by all kinds of things. You can use steam turbines that are driven by coal or nuclear energy, even renewables, hydroelectric, wind, tidal power.
Wow.
Even portable generators use internal combustion engines.
Oh, really?
It's all about converting that rotational energy into electrical energy.
Huh. Okay.
Yeah.
So the excerpt mentions something called electromagnetic induction.
Yes.
How does that fit in here?
Well, it's really the heart of it all. Because when that wire loop cuts through the magnetic field, it actually disturbs the field.
Uh-huh.
And that disturbance creates an electromotive force, which drives the current. So it's kind of like if you're pushing a swing.
Oh, okay.
The more force you apply, the higher the swing goes, right?
Yeah.
It's the same kind of principle.
So the faster the loop spins, the more voltage, the stronger the current.
Exactly.
Now, the excerpts also mention these terms like cycles and alternations, and then something called hertz. And I don't know, it seemed very like electrical vocabulary.
Yeah, a little bit.
Can you explain that stuff?
Okay, so think of it this way. One complete rotation of the generator's wire loop represents one cycle.
Okay.
And then each cycle has two halves, where the voltage swings from positive to negative and back again. Those are your alternations.
Okay.
And then hertz, it measures how many of these cycles happen each second.
Oh, I see.
So it's kind of like the beat or the rhythm of the AC.
Okay, so like if a generator completes 60 cycles in 1 second, that's 60 hertz? Is that how that works?
Exactly.
Yeah. And isn't 60 hertz like the standard for household power?
That's right. In the US and many other countries, 60 hertz is kind of the universal rhythm, you could say, for our electrical grid.
That's pretty cool.
Yeah.
Now, it also mentioned the sine wave, and it said that's the characteristic shape of an AC waveform.
Right.
What's so special about that shape?
Well, the sine wave is like a visual representation of how the voltage and current change smoothly over time in AC.
Okay.
So if you could actually see AC flowing, it would look like a wave gently rising and falling, crossing the zero line. as the current changes direction.
Ah.
It's really the heartbeat of AC. It shows its smooth and cyclical nature.
Okay, so the sine wave shows us the AC flow.
Right.
But the excerpts also talked about different ways to measure AC voltage, like peak voltage,
Yeah.
peak to peak voltage, and then effective voltage, or I think they said it was also called RMS voltage.
That's right.
What is all that about? Can you explain that without me needing to pull out a calculator?
Yeah, sure. Imagine a roller coaster.
Okay.
So peak voltage is like the highest point the roller coaster reaches. So it's the maximum positive or negative voltage in a cycle.
Okay.
Peak to peak voltage. Now that measures the total height of the roller coaster from its highest peak to its lowest valley. The total voltage difference between those extremes.
Okay, so peak is the single highest point, peak to peak is the whole height.
Exactly.
What about effective voltage?
So effective voltage, or RMS voltage, it's kind of like figuring out the average speed of that roller coaster ride, because even though the speed changes throughout the ride, we can calculate an average speed that represents the overall intensity of the ride.
Okay.
Similarly, RMS voltage tells us the equivalent DC voltage that would produce the same heating effect as our AC voltage.
So it's like the real measure of how much power that AC voltage has.
Yeah, it's like looking beyond just the peaks and valleys to understand the real power behind it all.
Okay, so when we see a voltage rating on something, like an appliance, it's usually referring to the RMS voltage.
That's right, not the peak voltage.
Okay.
Yeah, so RMS gives you the true measure.
Now, the excerpt also mentioned the relationship between period and frequency.
Okay.
Are those two sides of the same coin?
Yeah, they are. Think of a pendulum swinging back and forth.
Okay.
So the period is the time it takes for one complete swing,
Okay.
and the frequency is how many swings happen each second. The faster the swing, the shorter the period, and the higher the frequency.
Okay.
It's the same with AC.
I see.
Yeah.
So, high frequency AC signal, lots of short periods, low frequency signal, much longer periods.
Exactly.
Now, the excerpt, it kind of threw in a bit of a curveball because it mentioned that there are more AC waveforms than just the sine wave.
That's right.
It's that there's a whole family of these waveforms.
Yeah.
So what are these other waveforms and what makes them different from the sine wave?
Well, you've got square waves, triangular waves, sawtooth waves. They all have their own distinct shape and characteristics.
Huh, interesting.
Yeah, it's like comparing different musical instruments. They all create sound, but each one has its own unique timbre.
I can imagine how those different waveforms would look, even how they'd sound.
Yeah, it's quite remarkable. We'll be exploring those in much more detail in the next part of our deep dive.
Cool, I'm looking forward to that.
Yeah, but before we move on, let's delve into something called harmonics.
Harmonics, now that sounds like music theory.
It is connected to music.
Okay.
You know how a musical note is made up of a fundamental frequency and its harmonics, which give it that unique sound quality?
Yeah.
Well, AC signals, they can have harmonics too.
So is it the fundamental frequency is the main melody and the harmonics are the background vocals, kind of?
Exactly. They add depth and complexity, and just like different musical instruments produce different combinations of harmonics, different types of AC waveforms, they have their own unique harmonic profiles.
Oh, wow.
Yeah.
Are harmonics in AC just a theoretical thing, or do they actually do stuff?
No, they actually have real-world effects. Like, imagine you're trying to listen to your favorite song, but there's static and interference.
Right.
That's kind of what harmonics can do to electrical signals.
Oh, wow.
They can cause increased heating in equipment, reduce efficiency, even disrupt sensitive electronics.
So it's like noise in the electrical signal?
That's a good way to put it.
Okay.
And too much noise can really mess things up, especially in systems that rely on precise timing and clean signals.
So it's a well-tuned instrument produces a clear and pleasing sound. A well-managed AC system with minimal harmonics is essential for smooth and reliable operation.
Exactly.
Cool. So the excerpt also mentioned that AC power can be single-phase or three-phase.
That's right.
Does this have anything to do with the concept of phase that we talked about earlier?
It does. Remember how we compared phase to the timing of AC signals?
Right.
Well, in single-phase power, which is what you usually find in homes, there are two hot wires carrying AC voltage that are 180 degrees out of phase with each other, and then there's a neutral wire.
Oh.
Yeah. So the two hot wires are kind of are they synchronized but going in opposite directions? Exactly. And by connecting to one hot wire and the neutral, you get that standard 120 volts that's used for most household appliances.
Okay, but what about those appliances that need 240 volts, like a dryer or an oven?
Right.
How does that work with single-phase power?
Well, that's where those two hot wires working together come in.
Oh, okay.
So by connecting to both hot wires instead of just one,
Right.
you can tap into their combined voltage of 240 volts. So it's like having two power sources working together to give you that extra boost.
Oh, that's cool.
Yeah.
So what about three-phase power? Because the excerpt said that's used more in industrial settings.
Right, it's like having a trio of synchronized dancers, each 120 degrees out of phase with the others.
Oh, wow.
So instead of just two hot wires, you have three, and each one's carrying an AC signal that's offset in its timing.
Okay.
And that creates a continuous flow of power, where there's always current flowing in at least two of the phases.
So it's not just back and forth, it's constantly going.
Exactly, it's a constantly rotating wheel of energy.
Wow, so that makes it more efficient.
Much more efficient, especially for those heavy-duty equipment and motors. Also, that continuous flow means less vibration in the motors, so they run smoother and quieter.
Okay, so three-phase power, much better for industrial applications.
Yes, okay.
Now, the excerpt briefly mentioned these things called reactive components, like capacitors and inductors.
Yes.
What are those, and what do they do in AC circuits?
Well, think of them as energy storage units within the circuit.
Okay.
So capacitors store energy in an electric field, kind of like tiny rechargeable batteries. And inductors, they store energy in a magnetic field, so think of them like tiny electromagnets.
Okay, so they're like little reservoirs of energy, holding onto it and releasing it when needed.
Exactly.
How do they affect the AC current flowing through the circuit?
Well, that's where things get really interesting, because they can actually cause a shift in the timing between the voltage and the current in AC circuits.
Oh, really?
Yeah, it's like a dance where the partners aren't quite in sync.
So the voltage and the current aren't always peaking at the same time.
Exactly. And the amount of that time shift, or what we call the phase shift, it depends on the type of reactive component and its value.
Okay.
And this is really important to understand because this phase shift can actually affect the overall power delivered in an AC circuit.
So it's not just about how much voltage or current there is, but it's the timing.
The timing is critical.
That seems like it adds another layer of complexity.
It does.
So this phase shift, why should we care about it?
Well, the phase shift between voltage and current, it can actually impact how much power is delivered to a load.
Okay.
Think of two people trying to push a heavy object.
Right.
If they're not pushing at the same time, they're not going to be very effective.
Right.
Similarly, when voltage and current are out of phase, the power delivered to a device can be reduced.
That makes sense.
Yeah, so even if you have the right voltage and current levels, their timing relative to each other matters a lot.
Huh. So understanding this phase shift is really important for making things efficient, especially in those industrial settings where you've got those big machines that need a lot of power.
Exactly. As you delve deeper into electronics, you'll learn how to analyze and manipulate those phase relationships to design circuits that operate efficiently.
That's so cool. I'm starting to realize how much we take AC for granted.
It's true.
We just flip a switch, we expect the lights to come on, we don't think about all the stuff that's happening behind the scenes.
Yeah, it's a reminder that even those seemingly mundane things in our lives are built on these fascinating scientific principles.
Well, we covered a lot in this first part, from those basic principles of AC generation to the different types of waveforms, and even the world of harmonics.
It's a lot to take in.
Yeah.
But we're just getting started. The next part, we'll be looking into those non-sinusoidal waveforms, those unusual shapes that go beyond the sine wave. And we'll dig deeper into single-phase and three-phase power, their applications and their advantages.
Awesome.
Yeah.
Well, stay tuned. We're going to keep going deeper in the deep dive.
Absolutely.
All right, so welcome back to the deep dive. In the first part, we talked about all the basics of AC, like how it's generated,
Right, the cycles, the frequency.
The sine wave, all that good stuff.
Right.
So now we're going to go into the non-sinusoidal waveforms.
Yeah, these are the ones that kind of go beyond those smooth curves of a sine wave.
So we talked about square waves and triangular waves.
Right, and sawtooth waves.
Yeah, what makes those different?
Well, think of a sine wave like a gentle rolling hill, right?
Yeah,
A square wave, it's more like a set of stairs. It
Okay.
abruptly transitions between a high and a low state.
Yeah.
And that creates a distinct rectangular shape.
No smooth curves, just sharp corners.
Exactly.
Okay, so where do we see square waves, in the real world?
Well, think digital electronics. So your computer, your smartphone, all those signals that control them, they rely on these square waves to represent the ones and zeros, the digital information.
So they're like the backbone of the digital world?
Yeah, pretty much.
Okay, what about those triangular waves? What makes them unique?
Imagine a mountain range with perfectly straight slopes.
Okay.
It rises and falls smoothly, at a constant rate, forming a symmetrical triangle shape.
And what are they used for?
Well, you see them in all sorts of things, controlling the brightness of LEDs, generating test signals for audio equipment, certain types of amplifiers and oscillators.
Wow, okay, and what about sawtooth waves? Because that's a pretty interesting name.
Yeah, the sawtooth is kind of unique. It's like a voltage that rises steadily and then suddenly drops back down.
Oh, okay, so it's not symmetrical.
Not symmetrical, no.
Huh, so like up a ramp and then down a slide.
Exactly, like a Clyde.
And what are those used for?
Well, they're using music synthesizers a lot
Oh, cool.
to create those unique buzzing or rasping sounds.
Mm.
You'll also find them in things like, old CRT televisions
Oh, really?
and oscilloscopes.
So each of these waveforms has its own, purpose.
Exactly, its own distinct personality, you could say.
Now, we talked about single-phase and three-phase power, right? Can
Right.
you break down those key differences again and, why we use one over the other?
Sure, so think of single-phase power like a two-lane road with traffic going back and forth.
Got it.
That's what we typically see in homes, providing enough power for most appliances.
It's like our everyday electricity.
Yeah, it's the workhorse.
No, three-phase power.
That's like a superhighway, with 3 lanes of traffic flowing smoothly and continuously. Much more efficient for large amounts of power. So those big motors, industrial machines, that sort of thing.
So single phase is like a delivery truck, three phase is like a freight train.
Exactly, a high-speed freight train.
Now, we also talked about reactive components like capacitors and inductors.
Yes.
And how they can cause a phase shift between voltage and current. Can we go a little deeper into why that happens?
Yeah, so remember, capacitors store energy in an electric field,
Right, like little batteries.
and inductors store energy in a magnetic field, so tiny electromagnets.
Okay.
Well, that energy storage, it creates a kind of pushback against changes in voltage or current.
So they're resisting the flow?
In a way, yeah, capacitors don't like sudden changes in voltage, so they try to smooth things out.
Okay.
So in a circuit, they actually cause the current to lead the voltage.
Huh.
It's like, a dancer anticipating their partner's move and stepping ahead a little bit.
Okay, so the capacitor is ahead of the game?
Right now, inductors, they resist changes in current, so the voltage actually leads the current in that case.
Oh, okay, so it's the opposite.
It's the opposite. Yeah, it's like a dancer who's a little slow to react, always trailing a bit behind.
So why is this phase shift so important? What does it actually affect?
Well, it can really impact the power that's delivered to a load,
Okay.
because if the voltage and current aren't peaking at the same time, they're not working together efficiently.
Like pushing a heavy object.
Exactly. You need to be in sync.
So the timing of those peaks really matters.
It's critical for efficiency.
And I guess especially in those industrial settings.
Yeah, where you need to squeeze out every bit of performance.
This is making me think about AC in a whole new way. It's a lot more than just pushing electrons back and forth.
It really is. It's about timing, shapes, all these different components working together.
It's like a symphony.
A symphony of electricity, yeah.
So we went from those basic concepts to these different waveforms and now even phase shift. So where do we go from here?
Well, in the next part, we're going to bring it all together and look at some real-world applications of AC, from power grids to communications, even medical devices.
Oh, cool. I'm excited to hear about that.
Yeah, it's going to be fascinating to see how AC is all around us.
So stay tuned because we're going to keep diving deeper.
Absolutely.
All right, so welcome back to the deep dive. We've been talking all about AC, from the beginning, how it's generated.
The different waveforms,
Yeah,
the shift.
phase shifting.
Yeah, so now let's see how AC is actually used in the real world.
Right, because it's everywhere.
Yeah, so let's start big. How does AC power the electrical grid?
Well, think of the grid like a giant network of roads, transporting electricity from those power plants all the way to our homes and businesses.
Okay.
And AC is really the perfect vehicle for that long-distance travel.
Okay.
Because remember those transformers?
Right.
They let us step up the voltage for efficient transmission and then step it down again at the other end.
So it's like those electrical on-ramps and off-ramps, keeping everything flowing smoothly.
Exactly. And that ability to change voltage, that's really why AC won out over DC back in the day.
So it's still shaping our world today.
Oh, absolutely.
So beyond the grid, where else do we see AC making a difference?
Well, think about communication systems.
Oh, okay.
Remember those non-sinusoidal waveforms, those different shapes?
Well, they're essential for transmitting information, over radio waves, television signals, even fiber optic cables.
So those shapes are carrying our voices and music and videos all around the world.
They are. It's like a secret code embedded in those wave shapes, keeping us connected.
Wow, that's pretty cool.
It is. And here's another one. AC is crucial in a lot of medical devices, too.
Oh, okay, like what?
Well, you've got things like EKGs, those electrocardiograms.
Right?
They measure the heart's electrical activity,
Right.
and they rely on AC principles to pick up those tiny electrical signals and display them.
Oh, okay, so that's how doctors can see what's going on with the heart.
Exactly. It's like a window into the electrical workings of the body.
That's fascinating.
It is. And it's not just EKGs. There's MRI, EEG, all sorts of medical imaging and diagnostic tools that use AC in different ways.
So we've gone from power grids to communication systems to medical devices. AC is really everywhere.
It really is. And I think the most remarkable thing about it is its versatility. It can do so much, from powering our homes to transmitting information to helping doctors diagnose and treat patients.
It's amazing how much we rely on it every single day.
Absolutely. And as we've seen in this deep dive, understanding AC goes beyond just memorizing definitions.
Right.
It's about seeing how those concepts work together, those fundamental principles that make it all possible.
And how it impacts every aspect of our lives.
Exactly. It's like a puzzle, all those pieces fitting together.
So as we wrap up, I want to leave everyone with a thought. We talked about the flow of AC, the back and forth movement. But what if AC is also a metaphor for change? Like how our world is constantly changing and evolving.
That's interesting.
Just like AC is always shifting, our world is in a constant state of flux, adapting, reinventing itself.
That's a great point. Maybe those cycles and frequencies and waveforms, maybe they apply to more than just electricity.
Right, maybe they're part of bigger patterns like the rhythms of nature or even the universe.
Exactly. It makes you think.
Well, on that note, I think we've reached the end of our deep dive into the world of alternating current.
It's been quite a journey.
It has, and we hope you've learned a lot and maybe even gained a new appreciation for this amazing force that powers so much of our lives.
Absolutely. And remember, there's always more to explore, more to learn, so stay curious.
Thanks for joining us on the deep dive.